Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. Sedimentary rocks are defined, in the most general and perhaps most unremarkable of terms, as those rocks which have been formed through the gradual accumulation and subsequent consolidation of sediment, which is itself composed of fragments of pre-existing rocks, minerals, and organic materials that have been transported and deposited by water, wind, ice, or gravity over periods of time that are, by any human standard, extraordinarily and almost incomprehensibly long. It is estimated that approximately 75% of the rocks exposed at the surface of the Earth are sedimentary in origin, which is to say that the vast majority of the ground upon which one might walk, or upon which buildings and roads and other structures of human civilization have been erected, is composed of material that was, at some point in the geological past, loose and unconsolidated sediment resting at the bottom of an ocean, a lake, a river, or perhaps scattered across the surface of a desert by the slow and persistent action of wind. The formation of sedimentary rocks is a process that begins, as so many geological processes do, with the destruction of something that already exists. This initial phase is referred to as weathering, and it encompasses the various physical and chemical mechanisms by which solid rock is broken down into smaller and smaller pieces. Physical weathering, which is also sometimes called mechanical weathering, involves the disintegration of rock without any change to its chemical composition. This can occur through frost wedging, in which water seeps into cracks in the rock and subsequently freezes, expanding by approximately 9% in volume and thereby exerting tremendous pressure on the surrounding rock, which may amount to pressures of up to 207 megapascals under ideal conditions. Over many cycles of freezing and thawing, which may number in the thousands or tens of thousands over the course of centuries, the rock is gradually pried apart and reduced to smaller fragments. Another form of physical weathering is known as thermal expansion, in which the repeated heating and cooling of rock causes differential expansion and contraction of the mineral grains within it, eventually leading to the development of fractures and the spalling off of thin sheets of rock from the surface, a process that is sometimes referred to as exfoliation. In desert environments, where daytime temperatures may reach 45 degrees Celsius and nighttime temperatures may fall to near freezing, this process can be particularly effective over long periods of time. Biological weathering, which occupies a somewhat intermediate position between physical and chemical weathering, occurs when the roots of plants grow into cracks in rock and gradually widen them, or when burrowing organisms such as earthworms or termites physically displace and break apart rock and soil. It has been estimated that earthworms in temperate environments can move between 7 and 18 metric tons of soil per hectare per year through their burrowing activities. Chemical weathering, on the other hand, involves the alteration of the chemical composition of minerals within the rock through reactions with water, oxygen, carbon dioxide, and various acids. The most common form of chemical weathering is hydrolysis, in which water reacts with silicate minerals to produce clay minerals. For example, The mineral feldspar, which is the most abundant mineral group in the Earth's crust, comprising approximately 60% of all crustal rocks, reacts with slightly acidic water to form kaolinite, a clay mineral. Along with dissolved silica and various cations such as potassium, sodium, or calcium, depending on the specific type of feldspar involved. This reaction proceeds slowly under normal surface conditions, with the rate being influenced by factors such as temperature, the pH of the water, and the surface area of the mineral grains exposed to the water. Oxidation is another important chemical weathering process, particularly for iron-bearing minerals. When minerals such as olivine, pyroxene, or biotite are exposed to oxygen and water, the iron within them is oxidized from its ferrous state to its ferric state, producing iron oxide minerals such as hematite and goethite, which impart the characteristic reddish-brown coloration often observed in weathered rock surfaces and soils. The process of carbonation involves the reaction of carbon dioxide with water to form carbonic acid, which then reacts with carbonate minerals such as calcite, the primary mineral in limestone, to produce calcium bicarbonate, which is soluble in water. This is the process by which limestone caves and karst landscapes are formed over periods of tens of thousands to millions of years. With the dissolution rate of limestone by carbonic acid being approximately 5 to 30 millimeters per thousand years in most temperate environments, depending on the amount of rainfall and the concentration of carbon dioxide in the soil. Once weathering has reduced solid rock to smaller fragments and dissolved ions, the process of erosion begins. Erosion is the transport of these weathered materials from one location to another by the action of moving water, wind, ice, or gravity. Running water is by far the most significant agent of erosion on the Earth's surface, and it has been estimated that rivers transport approximately 20 billion metric tons of sediment to the world's oceans each year. The amount of sediment that a river can transport is dependent upon its velocity and discharge, with faster-flowing rivers being capable of carrying larger and heavier particles. The relationship between water velocity and particle size transport is described by the Joulstrom diagram, which was first published by the Swedish geomorphologist Philip Joulstrom in 1935. And which demonstrates that the velocity required to erode a particle is greater than the velocity required to transport it, and that both of these velocities increase with increasing particle size. Although very fine clay particles require relatively high velocities to erode due to the cohesive forces between them. Wind erosion is particularly effective in arid and semi-arid environments, where vegetation cover is sparse and loose sediment is exposed at the surface. Wind can transport sediment through three primary mechanisms: suspension, in which very fine particles, typically less than 70 micrometers in diameter, are lifted high into the air and carried for great distances, sometimes thousands of kilometers. Saltation, in which sand-sized particles, typically between 70 micrometers and 500 micrometers, bounce along the surface in a series of short hops, and surface creep, in which larger particles are pushed along the surface by the Impact of saltating grains. Glacial erosion occurs when glaciers, which are large masses of ice that move slowly under the influence of gravity, scrape and pluck rock from the underlying bedrock and transport it, sometimes for distances of hundreds of kilometers. It has been estimated that the Antarctic ice sheet, which covers an area of approximately 14 million square kilometers and has an average thickness of approximately 2.16 kilometers, contains approximately 26.5 million cubic kilometers of ice. The deposition of sediment occurs when the transporting medium, whether it be water, wind, or ice, loses its capacity to carry the sediment further. In the case of rivers, this typically occurs when the velocity of the water decreases, which may happen when a river enters a lake or the ocean, when it flows over a sudden decrease in gradient, or when its discharge decreases during periods of low rainfall. The resulting deposits of sediment are arranged in a predictable pattern, with the largest and heaviest particles being deposited first, and the finest particles being carried the farthest before settling out. This process of size sorting is a fundamental characteristic of many sedimentary deposits and is one of the features that geologists use to interpret the conditions under which the sediment was deposited. In marine environments, sediment is deposited on the continental shelf, the continental slope, and the abyssal plain, with the finest sediment, such as clay and silt, being carried the farthest from shore before settling to the ocean floor. The rate of sediment accumulation on the deep ocean floor is remarkably slow, typically on the order of 1 to 5 millimeters per 1,000 years, which means that a layer of sediment only 1 meter thick may represent 1,000,000 years or more of continuous deposition. Following deposition, the sediment undergoes a series of physical and chemical changes collectively referred to as lithification, which is the process by which loose, unconsolidated sediment is transformed into solid rock. The first stage of lithification is compaction, in which the weight of overlying sediment compresses the deeper layers, squeezing out water and reducing the pore space between the grains. In muddy sediments, which may initially have a porosity of 60 to 80%, compaction alone can reduce the porosity to 10 to 30%. The second stage is cementation, in which dissolved minerals precipitate from groundwater flowing through the pore spaces and bind the sediment grains together. The most common cementing agents are silica, calcite, and iron oxide, each of which imparts different properties to the resulting rock. Silica cement produces the hardest and most resistant rocks, while calcite cement can be dissolved by acidic groundwater over time, and iron oxide cement gives the rock a characteristic reddish or brownish color. Sedimentary rocks are broadly classified into 3 main categories based on their mode of formation: clastic sedimentary rocks, chemical sedimentary rocks, and organic sedimentary rocks. Clastic sedimentary rocks, which are also sometimes referred to as detrital sedimentary rocks, are composed of fragments or clasts of pre-existing rocks that have been weathered, eroded, transported, deposited, and lithified. These are the most common type of sedimentary rock and include such well-known varieties as sandstone, shale, and conglomerate. The classification of clastic sedimentary rocks is based primarily on the size of the clasts, which can range from boulders larger than 256 millimeters in diameter down to clay particles smaller than 4 micrometers, which is to say smaller than 3.9 micrometers according to the Wentworth grain size scale, which was established by Chester K. Wentworth in 1922 and remains the standard classification system used by geologists today. Chemical sedimentary rocks are formed through the precipitation of dissolved minerals from water, typically in environments where evaporation rates are high or where changes in water chemistry cause minerals to become insoluble and precipitate out of solution. Examples of chemical sedimentary rocks include limestone, which can form through both chemical and organic processes, dolostone, chert, and the various evaporite minerals such as halite and gypsum. The formation of chemical sedimentary rocks is governed by the principles of chemical equilibrium and solubility, and the specific minerals that precipitate are determined by the chemical composition and temperature of the water, as well as the rate of evaporation. Organic sedimentary rocks are composed primarily of the remains of once living organisms or of material produced by biological processes. Coal, which is formed from the accumulation and compaction of plant material in swampy environments, is the most widely known example of an organic sedimentary rock, and it has been estimated that a layer of coal 1 meter thick represents the accumulation and compaction of approximately 10 meters of original plant material over a period of thousands of years. Other examples of organic sedimentary rocks include certain types of limestone, such as coquina, which is composed almost entirely of shell fragments, and chalk, which is composed of the microscopic shells of marine organisms called coccolithophores, each of which measures only 2 to 25 micrometers in diameter. The rock cycle is the conceptual framework that describes the continuous transformation of rocks from one type to another through various geological processes over immense spans of time. The concept was first articulated by the Scottish geologist James Hutton in 1788 in his landmark work Theory of the Earth, and it remains a fundamental principle of modern geology. According to the rock cycle, sedimentary rocks can be transformed into metamorphic rocks through the application of heat and pressure deep within the Earth's crust, and metamorphic rocks can be melted to form magma, which upon cooling and solidification produces igneous rocks. These igneous rocks, in turn, can be weathered and eroded to produce sediment, which is then deposited and lithified to form new sedimentary rocks, thereby completing the cycle. It should be noted, however, that the rock cycle is not a rigid, sequential process, and rocks can follow many different pathways through the cycle. For instance, sedimentary rocks can be weathered and eroded without ever being metamorphosed or melted, producing new sedimentary rocks directly from old ones, and igneous rocks can be metamorphosed without first being weathered into sediment. Sedimentary basins are regions of the Earth's crust where sediment accumulates to significant thicknesses over long periods of geological time. These basins are formed through various tectonic processes that create topographic depressions in the Earth's surface, and they are the primary settings in which thick sequences of sedimentary rocks are preserved. The largest sedimentary basins can be thousands of kilometers across and contain sedimentary deposits tens of kilometers thick, representing hundreds of millions of years of continuous or near-continuous sedimentation. There are several types of sedimentary basins, each of which is associated with a particular tectonic setting. Rift basins are formed when the Earth's lithosphere is stretched and pulled apart, typically at divergent plate boundaries, creating a central depression, or graben, that is bounded by normal faults. The East African Rift System, which extends for approximately 3,500 kilometers from the Afar Depression in Ethiopia to Mozambique, is a modern example of a continental rift basin, and it contains sedimentary deposits up to several kilometers thick. Passive margin basins form along the edges of continents that are not associated with active tectonic plate boundaries, such as the eastern coast of North America. These basins accumulate sediment delivered by rivers from the continental interior, and they can contain sedimentary sequences more than 15 kilometers thick, as is the case with the sedimentary deposits underlying the Gulf of Mexico. Foreland basins are formed on the continental side of mountain belts, where the weight of the mountains causes the adjacent crust to flex downward, creating a depression that is then filled with sediment eroded from the mountains. The Gangetic Plain of northern India, which lies south of the Himalaya Mountains, is an example of a foreland basin, and it contains sedimentary deposits up to 6 kilometers thick. Intercratonic basins are broad, shallow depressions that form within the stable interior of continents, far from any active plate boundary. The mechanisms by which these basins form are not entirely understood, but they may be related to slow subsidence of the crust due to cooling of the underlying lithosphere or to ancient tectonic events that weaken the crust. The Michigan Basin, which underlies much of the state of Michigan in the United States, is an example of an intracratonic basin, and it contains a roughly circular sequence of sedimentary rocks up to approximately 4.8 kilometers thick, deposited over a period of more than 400 million years. The Williston Basin, which underlies parts of Montana, North Dakota, South Dakota, Saskatchewan, and Manitoba, is another intracratonic basin containing sedimentary deposits up to approximately 4.9 kilometers thick. The study of sedimentary rocks and the processes by which they are formed constitutes a significant portion of the discipline of geology, and it has practical implications for a wide range of human activities, including the exploration for and extraction of fossil fuels, the assessment and remediation of groundwater resources, the reconstruction of past climates and environments, and the prediction of future geological hazards. The slow and methodical examination of sedimentary rocks, their mineral compositions, their textures, their structures, and the fossils they contain, has, over the course of more than 2 centuries of scientific investigation, revealed an astonishingly detailed record of the Earth's history, stretching back more than 4 billion years to the earliest known sedimentary deposits, which are found in the Isua supercrustal belt of southwestern Greenland and have been dated to approximately 3 0.8 billion years before the present. These ancient rocks, though heavily metamorphosed, still preserve evidence of the sedimentary processes that formed them, including graded bedding and cross-lamination, which are indicative of deposition by flowing water in a marine environment that existed on the young Earth long before the appearance of the first complex life forms. The sheer volume of sedimentary rock that has been produced over the course of Earth's history is, in a word, staggering. It has been estimated that the total volume of sedimentary rock in the Earth's crust is approximately 1.1 times 10 to the 9th cubic kilometers, which, if spread evenly over the entire surface of the Earth, would form a layer approximately 2.2 kilometers thick. Of this total, approximately 73% is mudstone and shale, approximately 15% is sandstone, and approximately 12% is carbonate rock, which includes limestone and dolostone. These proportions reflect the fact that fine-grained sediment, which is the precursor to mudstone and shale, is the most abundant product of weathering and is produced in greater quantities than coarser sediment in most environments. The dominance of fine-grained sedimentary rocks is a consequence of the fact that most weathering produces clay minerals, which are the finest-grained products of chemical weathering, and that these clay minerals are easily transported in suspension by water and wind and are deposited in the quietest, most distal environments, where they accumulate in vast quantities over geological time. The composition of the sediment that accumulates in a sedimentary basin is influenced by a number of factors, including the lithology of the source rocks from which the sediment was derived, the climate and weathering regime under which those source rocks were broken down, the distance and mode of transport from the source to the depositional site, and the chemical conditions that prevail in the depositional environment itself. In tropical regions, where temperatures are high and rainfall is abundant, chemical weathering is intense, and the resulting sediment tends to be enriched in clay minerals, particularly kaolinite, and depleted in chemically unstable minerals such as feldspar and ferromagnesian silicates. In contrast, in cold or arid regions, where physical weathering predominates over chemical weathering, the sediment tends to retain a greater proportion of unstable minerals because the conditions for their chemical decomposition are less favorable. The mineralogical maturity of a sediment, which is a measure of the extent to which unstable minerals have been removed by weathering and transport, is thus a reflection of the intensity and duration of the weathering processes to which the source material was subjected. The concept of provenance, which refers to the geographic and geological origin of the sediment in a sedimentary rock, is a subject of considerable interest in sedimentary geology, as it provides information about the tectonic setting and the geological history of the source area. Provenance analysis is typically carried out by examining the mineral composition of the sediment, particularly the types and proportions of heavy minerals, which are minerals with a specific gravity greater than approximately 2.85 and which are present in most sedimentary rocks in small but measurable quantities. Common heavy minerals found in sedimentary rocks include zircon, tourmaline, rutile, garnet, staurolite, kyanite, sillimanite, epidote, and hornblende. And the specific assemblage of heavy minerals present in a sediment is determined by the types of rocks in the source area and the weathering and transport conditions. Zircon, tourmaline, and rutile are particularly resistant to both chemical weathering and physical abrasion, and their relative abundance in a sediment increases with increasing mineralogical maturity, a relationship that is quantified by the ZTR index, which is the percentage of these three minerals in the total heavy mineral assemblage. The rate of sedimentation varies enormously from one environment to another and from one geological period to another. In the deep ocean, far from any source of terrestrial sediment, the accumulation rate of pelagic sediment, which consists primarily of the shells of planktonic organisms and wind-blown dust, is typically on the order of 1 to 10 millimeters per thousand years. On continental margins, where rivers deliver large quantities of sediment to the coast, sedimentation rates can be several orders of magnitude higher, reaching values of 100 to 1,000 millimeters per thousand years, or even higher during periods of particularly high sediment supply, such as during glacial periods when increased erosion of glaciated landscapes delivers large volumes of sediment to the adjacent seas. In delta environments, where rivers deposit their sediment load at the coast, sedimentation rates can be even higher still, with values of several meters per thousand years being not uncommon. The Mississippi River Delta, for example, has been prograding or building outward into the Gulf of Mexico at a rate that has varied over time, but has resulted in the accumulation of sedimentary deposits more than 12 kilometers thick since the beginning of the Cenozoic era, approximately 66 million years ago. It is, perhaps, worth noting at this point that the study of sedimentary rocks is not merely an academic exercise, though it is certainly that as well. The economic significance of sedimentary rocks cannot be overstated, for it is within these rocks that virtually all of the world's petroleum and natural gas are found, trapped in the pore spaces of sandstones and limestones and sealed beneath impermeable layers of shale and evaporites. Approximately 99% of the world's fossil fuel resources are contained within sedimentary rocks, and the exploration for and production of these resources is a multi-trillion-dollar global industry that employs millions of people and provides the energy upon which modern industrial civilization depends. Coal, which is itself a sedimentary rock, remains the single largest source of electricity generation worldwide, accounting for approximately 36% of global electricity production as recently as 2022. Sedimentary rocks also serve as the principal aquifers from which groundwater is extracted for drinking water, irrigation, and industrial use, with approximately 2 billion people worldwide depending on groundwater as their primary source of fresh water. And so, with these preliminary observations in mind, one may begin to appreciate, or at least to acknowledge, the fundamental importance of sedimentary rocks to both the scientific understanding of the Earth and to the practical concerns of human civilization. The processes by which these rocks are formed, the minerals and structures they contain, and the stories they tell about the ancient environments in which they were deposited are subjects of considerable depth and complexity. And it is to a more detailed examination of these topics that the following discussion shall now, slowly and methodically, turn its attention, proceeding through the various types of sedimentary rocks, their characteristics, their origins, and their significance. In a manner that is, one hopes, thorough and informative, if perhaps not entirely exciting. Clastic sedimentary rocks, as has been previously mentioned, are those rocks which are composed of fragments or clasts derived from the weathering and erosion of pre-existing rocks, and they constitute, by volume, the most abundant category of sedimentary rocks found at the Earth's surface. The classification of clastic sedimentary rocks is based primarily upon the size of the constituent clasts, and the standard system of grain size classification used in geology is the Wentworth scale, which was published by Chester K. Wentworth in 1922 in the Journal of Geology, Volume 30, pages 377 through 392. The Wentworth scale divides clastic particles into a series of size categories, each of which differs from the adjacent categories by a factor of 2. A geometric progression that has proven to be remarkably useful in the description and comparison of sedimentary deposits across a wide range of environments and geological settings. According to the Wentworth scale, the largest classed category is boulders, which are defined as particles larger than 256 millimeters in diameter. Cobbles range from 64 to 256 millimeters, pebbles from 4 to 64 millimeters, granules from 2 to 4 millimeters, and sand from 1/16 of a millimeter, or 62.5 micrometers, to 2 millimeters. Sand is further subdivided into very coarse sand, which ranges from 1 to 2 millimeters, coarse sand from 0.5 to 1 millimeter, medium sand from 0.25 to 0.5 millimeters, fine sand from 0.125 to 0.25 millimeters, and very fine sand from 0.0625 to 0.125 millimeters. Silt ranges from 3.9 micrometers to 62.5 micrometers, and clay is defined as any particle smaller than 3.9 micrometers. It should be noted that in geology, the term clay refers to a grain size category and not to a specific mineral, although clay-sized particles are most commonly composed of clay minerals such as kaolinite, aelite, and montmorillonite. In 1934, the American geologist William C. Crumbine introduced the phi scale, which is a logarithmic transformation of the Wentworth scale in which the grain diameter in millimeters is converted to a dimensionless number using the formula phi equals negative log base 2 of the diameter in millimeters. On this scale, a grain diameter of 1 millimeter corresponds to a phi value of 0. A diameter of 2 millimeters corresponds to a phi value of -1. A diameter of 0.5 millimeters corresponds to a phi value of +1, and so forth. The phi scale has the advantage of converting the geometric progression of the Wentworth scale into an arithmetic progression, which greatly simplifies the statistical analysis of grain size distributions and allows for the calculation of meaningful statistical parameters such as the mean grain size, the standard deviation, the skewness, and the kurtosis of a sediment sample. The coarsest clastic sedimentary rocks are the conglomerates and breccias, which are composed of clasts larger than 2 millimeters in diameter. Conglomerates are distinguished from breccias by the shape of their clasts. Conglomerates contain rounded to subrounded clasts, which indicates that the clasts have been transported a significant distance and have been abraded and smoothed by the action of water or wind during transport, while breccias contain angular to subangular clasts, indicating relatively short transport distances and limited abrasion. Conglomerates are commonly found in high-energy environments such as alluvial fans, river channels, and beaches, where the water velocity is sufficient to transport large particles. The matrix of a conglomerate, which is the finer-grained material that fills the spaces between the larger clasts, is typically composed of sand or a mixture of sand and finer sediment. The cement that binds the clasts and matrix together may be composed of silica, calcite, or iron oxide, depending on the chemical composition of the groundwater that has percolated through the deposit. Sandstone is perhaps the most widely recognized and studied of all clastic sedimentary rocks, and it is defined as a rock composed primarily of sand-sized grains, which is to say grains ranging from 62.5 micrometers to 2 millimeters in diameter. Sandstones are classified on the basis of both their grain composition and the amount and type of matrix material they contain. The most commonly used classification system for sandstones is that of Robert L. Folk, which was published in 1974 and which divides sandstones into categories based on the relative proportions of 3 end-member grain types: quartz, feldspar, and lithic fragments. A sandstone composed of more than 95% quartz grains is classified as a quartz-arnite, which is the most compositionally mature type of sandstone and indicates extensive weathering, transport, and recycling of the source material. A sandstone containing more than 25% feldspar grains is classified as an arkose, and such rocks are typically derived from the weathering of granitic or gneissic source rocks and are commonly found in close proximity to their source areas. As feldspar is relatively susceptible to chemical weathering and does not survive long distances of transport. A sandstone containing more than 25% lithic fragments is classified as a lithoronite, and these fragments may be composed of any type of pre-existing rock, including volcanic, sedimentary, or metamorphic rock. An additional distinction in sandstone classification is made between aaronites and wax. Aaronites are sandstones that contain less than 15% matrix, which is defined as material finer than 30 micrometers, while wax contain more than 15% matrix. Wax, which are also sometimes referred to as gray wax, are characterized by their dark color and poorly sorted texture, and they are typically deposited by turbidity currents in deep marine environments. The term greywack has been in use since at least the 18th century, having been derived from the German word grauwack, and it refers to a specific type of dark, hard, poorly sorted sandstone that was first described in the Harz Mountains of Germany. Siltstone is a clastic sedimentary rock composed primarily of silt-sized grains, which range from 3.9 to 62.5 micrometers in diameter. Siltstones are finer grained than sandstones, but coarser than mudstones and shales, and they are typically deposited in environments of intermediate energy, such as floodplains, shallow marine settings, and the distal portions of deltas. Siltstones are commonly laminated, displaying thin, parallel layers that reflect variations in the supply of sediment and the energy of the depositing medium over time. The individual grains in a siltstone are too small to be seen with the unaided eye, but can be detected by the slightly gritty texture that is felt when the rock is rubbed between the fingers. A simple field test that has been used by geologists for generations to distinguish siltstones from the still finer-grained mudstones and shales. Shale is the most abundant sedimentary rock type on Earth, constituting approximately 45 to 55% of all sedimentary rocks by some estimates, and it is composed primarily of clay-sized particles, which are less than 3.9 micrometers in diameter. The defining characteristic of shale, as distinct from mudstone, is its facility, which is the tendency to split along thin, roughly parallel planes that are oriented parallel to the bedding. This facility is a consequence of the preferred alignment of platy clay mineral grains, which tend to settle with their flat surfaces oriented parallel to the depositional surface, and which become further aligned during compaction as the overlying sediment compresses the deposit and squeezes out water. Mudstone, by contrast, is a fine-grained sedimentary rock that lacks facility and instead breaks along irregular, blocky fractures. Both shale and mudstone are deposited in low-energy environments where fine sediment can settle out of suspension, such as deep ocean basins, lakes, lagoons, and the distal portions of river floodplains. The composition of shale is dominated by clay minerals, which typically make up 40 to 60% of the rock by weight, with quartz silt comprising approximately 20 to 30%, feldspar 5 to 10%, and various other minerals, including mica, calcite, dolomite, pyrite, and organic matter, making up the remainder. The specific assemblage of clay minerals present in a shale is determined by the composition of the source rocks, the climate and weathering conditions under which the source rocks were broken down, and the diagenetic changes that have occurred after deposition. In humid tropical environments, intense chemical weathering tends to produce kaolinite-rich clays, while in cooler, drier environments, illite and chlorite are more commonly produced. Smectite, which is a group of expandable clay minerals that includes montmorillonite, is commonly derived from the weathering of volcanic ash and is a characteristic component of shales deposited in regions with significant volcanic activity. The sorting of a clastic sedimentary rock refers to the degree of uniformity in the grain sizes present within the rock. A well-sorted sediment is one in which all of the grains are approximately the same size, while a poorly sorted sediment contains a wide range of grain sizes. Sorting is a reflection of the transport and depositional processes that produce the sediment, Well-sorted sediments are typically produced by sustained transport in a single medium, such as wind or waves, which selectively separates grains by size, while poorly sorted sediments are typically produced by processes that transport a wide range of grain sizes simultaneously, such as glacial ice or debris flows. Beach sands, for example, are typically very well sorted, with standard deviations of less than 0.55 units, because the persistent back-and-forth action of waves effectively separates the grains by size. Glacial till, by contrast, is typically very poorly sorted, with standard deviations of 2 phi units or more, because glacial ice is capable of transporting particles ranging in size from clay to boulders without any size discrimination. The rounding of clasts is another important textural property of clastic sedimentary rocks, and it refers to the degree to which the edges and corners of individual grains have been smoothed and abraded during transport. Angular grains have sharp, well-defined edges and corners, while well-rounded grains are smooth and nearly spherical in outline. The degree of rounding increases with the distance and duration of transport, as well as with the energy of the transporting medium. A grain of quartz sand that has been transported by wind in a desert environment for a long period of time will typically be more rounded than a grain of the same size that has been transported a similar distance by water. Because the collisions between grains in air are more energetic than those in water, due to the lower viscosity and density of air compared to water. The measurement of rounding is typically performed by visual comparison with standard charts, such as the Powers Roundness Scale, which was published by Maurice C. Powers in 1953, and which defines 6 categories of roundness: very angular, angular, subangular, subrounded, rounded, and well-rounded. Depositional environments are the specific settings on the Earth's surface or beneath the sea in which sediment accumulates, and the characteristics of the sediment deposited in a particular environment are strongly influenced by the physical, chemical, and biological conditions that prevail there. Fluvial environments, which encompass all environments associated with rivers and streams, are among the most important settings for the deposition of clastic sediment. River channels deposit relatively coarse-grained sediment, such as gravel and sand, in bars and on the channel floor, while floodplains, which are the flat areas adjacent to the channel that are periodically inundated during floods, accumulate finer-grained sediments such as silt and clay. The deposits of meandering rivers are characterized by a distinctive vertical sequence known as a fining upward sequence, in which coarse channel deposits at the base grade upward into finer-grained floodplain deposits at the top. This sequence is produced by the lateral migration of the river channel across its floodplain, which causes the coarse channel deposits to be overlain by the fine floodplain deposits as the channel moves away. Marine environments, which include all settings within the world's oceans, are the most extensive depositional environments on Earth, covering approximately 71% of the planet's surface. The continental shelf, which extends from the shoreline to a depth of approximately 130 meters, is a relatively shallow, gently sloping platform that receives sediment from rivers and from the erosion of the adjacent coast. The sediment on the continental shelf is typically a mixture of sand, silt, and clay, with the coarsest material concentrated near the shore and the finest material deposited farther offshore. The continental slope, which descends from the edge of the continental shelf to a depth of approximately 2,000 to 3,000 meters, is a steeper surface down which sediment is transported by gravity-driven processes, such as turbidity currents. These currents are dense, sediment-laden flows that travel at speeds of up to several tens of kilometers per hour, and can transport large volumes of sediment from the shelf edge to the deep ocean floor, where it is deposited as submarine fans that may extend for hundreds of kilometers across the abyssal plain. Aeolian environments, or environments dominated by wind, are significant settings for sediment transport and deposition in arid and semi-arid regions. The most characteristic feature of aeolian environments is the sand dune, which is a mound or ridge of sand that has been shaped by the wind. Sand dunes can take a variety of forms, depending on the wind regime, the supply of sand, and the amount of vegetation present. Barcon dunes are crescent-shaped dunes that form in areas with a limited sand supply and a relatively constant wind direction, with their horns pointing downwind. Transverse dunes are long, straight ridges oriented perpendicular to the prevailing wind direction, and they form in areas with an abundant sand supply. Star dunes, which have a roughly pyramidal shape with 3 or more arms radiating from a central peak, form in areas where the wind blows from multiple directions. The largest sand dunes on Earth can be found in the Rub al Khali, or empty quarter, of the Arabian Peninsula, where star dunes may reach heights of more than 300 meters above the surrounding terrain. Glacial environments are associated with the formation, movement, and melting of glaciers and ice sheets, and they produce a distinctive suite of sedimentary deposits. As mentioned previously, glacial till is a poorly sorted deposit composed of a mixture of grain sizes ranging from clay to boulders, and it is deposited directly by the glacier without reworking by water or wind. Glaciofluvial deposits are those that have been transported and deposited by meltwater streams flowing from the glacier, and these deposits are typically better sorted than till because the flowing water selectively transports particles by size. Glaciolacustrine deposits are fine-grained sediments that accumulate in lakes formed by glacial meltwater, and they are often characterized by rhythmic laminations known as varves, which consist of alternating layers of silt and clay that are deposited on a seasonal cycle, with the coarser silt layer representing summer deposition when meltwater input is high, and the finer clay layer representing winter deposition when the lake is frozen, and only the finest particles settle out of suspension. Each varve pair represents 1 year of deposition, and sequences of varves can be counted to determine the duration of glacial lake sedimentation, a technique that has been used to establish chronologies spanning thousands of years. Sedimentary structures are features within or on the surface of sedimentary rocks that provide information about the conditions under which the sediment was deposited. Cross-bedding, which is also referred to as cross-stratification, is one of the most common and informative sedimentary structures, and it consists of inclined layers of sediment that are oriented at an angle to the main horizontal bedding planes. Cross-bedding is produced by the migration of bed forms such as ripples and dunes across the depositional surface. As sediment is transported over the crest of a dune or ripple and deposited on the lee, or downwind or downcurrent side, it forms inclined layers known as foresets that dip in the direction of current or wind flow. The angle of the foresets, the thickness of the cross-bedded units, and the pattern of the cross-bedding can be used to determine the velocity and direction of the current or wind that produce the structure, as well as the depth of the water in which it was deposited, if applicable. Tabular cross-bedding, in which the cross-bedded sets are bounded by flat, parallel surfaces, is commonly produced by the migration of straight-crested dunes in rivers and shallow marine environments. Trough cross-bedding, in which the sets are bounded by curved, trough-shaped surfaces, is produced by the migration of three-dimensional, sinuous crested dunes. Ripple marks are another common sedimentary structure, and they are small, undulating features on the bedding surface that are produced by the action of flowing water or wind on sediment. Current ripples are asymmetric, with a gently sloping upstream side and a steeper downstream side, and they indicate the direction of current flow. Wave ripples are symmetric, with equal slopes on both sides of the crest, and they are produced by the oscillatory motion of water beneath waves. Ripple marks are typically small, with wavelengths of a few centimeters to a few tens of centimeters and heights of a few millimeters to a few centimeters. Graded bedding is a structure in which the grain size within a single bed decreases from bottom to top, indicating deposition from a waning current or from a turbidity current in which the largest, heaviest particles settled out first, and the finest particles settled last. The presence of graded bedding in a sedimentary sequence is a strong indicator of deposition by turbidity currents in a deep marine environment. Mud cracks, which are also known as desiccation cracks, are polygonal fractures that form in fine-grained sediment, such as mud or clay, when it dries out and contracts. These cracks typically form a pattern of intersecting fractures that divide the surface into irregular polygonal blocks, and they are a reliable indicator that the sediment was exposed to the atmosphere and dried out before being buried by subsequent deposits. The presence of mud cracks in a sedimentary rock sequence is therefore evidence that the depositional environment was subject to periodic drying, which is characteristic of environments such as tidal flats, playas, and ephemeral lake beds. Sole marks are features preserved on the bottom surfaces of sandstone beds that were originally formed on the underlying mud surface before the sand was deposited. They include flute casts, which are elongated, spoon-shaped depressions that taper in the upstream direction and indicate the direction of current flow, and groove casts, which are long. Straight ridges on the base of the sandstone bed that were formed when objects such as pebbles or pieces of wood were dragged across the mud surface by the current. Bioturbation refers to the disruption of primary sedimentary structures by the activities of organisms, including burrowing, feeding, and locomotion. In many marine sedimentary environments, bioturbation is so intense that it completely destroys the original layering and produces a homogeneous, structureless sediment. The degree of bioturbation is typically assessed using the ichnofabric index, which ranges from 1, indicating no bioturbation and perfectly preserved primary sedimentary structures, to 6, indicating complete bioturbation with no original structures remaining. The study of trace fossils, which are the preserved evidence of organism activities such as burrows, tracks, and trails, is known as ichnology, and it provides valuable information about the organisms that inhabited ancient sedimentary environments, even when no body fossils are preserved. The Scolithos ichnofacies, which is characterized by vertical burrows, is typically associated with high-energy, shallow marine environments such as beaches and shore faces, while the Cruziana ichnofacies, characterized by horizontal feeding traces, is typical of lower-energy, deeper marine shelf environments. The study of the textures and structures of clastic sedimentary rocks, combined with the analysis of their mineral composition and fossil content, allows geologists to reconstruct the depositional environments in which these rocks were formed and to interpret the geological history of the regions in which they are found. This process of environmental interpretation, known as facies analysis, is one of the most fundamental and widely practiced activities in sedimentary geology, and it has applications in fields ranging from petroleum exploration to paleoclimatology to natural hazard assessment. The methodical examination of grain size, sorting, rounding, composition, sedimentary structures, and fossil assemblages, when considered together, provides a remarkably detailed picture of the conditions that prevailed at the time and place of deposition. And it is through this careful and systematic analysis that the long and complex history of the Earth's surface environments has been gradually reconstructed over the past 2 centuries of geological investigation. Chemical sedimentary rocks, which represent the second major category of sedimentary rocks, are formed not from the accumulation of solid fragments of pre-existing rocks, as is the case with clastic sedimentary rocks, but rather from the precipitation of dissolved minerals out of solution, a process that is governed by the fundamental principles of chemical thermodynamics and the behavior of ions in aqueous systems. The conditions under which chemical precipitation occurs are varied and include evaporation of water, changes in water temperature or pressure, changes in the pH or oxidation state of the water, and biological activities that alter the local chemical environment. The resulting rocks are composed of interlocking crystals of the precipitated mineral or minerals, and they are typically classified according to their dominant mineral composition. Limestone is by far the most abundant and widely distributed chemical sedimentary rock, and it is composed primarily of the mineral calcite, which is calcium carbonate with the chemical formula CaCO3. Limestone can form through both purely chemical and organic processes, and in practice, most limestones contain a mixture of chemically precipitated and biologically produced calcite. The chemistry of calcite precipitation is governed by the carbonate equilibrium system, which describes the relationships between carbon dioxide, carbonic acid, bicarbonate ions, carbonate ions, and calcium ions in aqueous solution. When carbon dioxide dissolves in water, it reacts with the water to form carbonic acid, which then dissociates to produce hydrogen ions and bicarbonate ions. Bicarbonate ions can further dissociate to produce hydrogen ions and carbonate ions. The precipitation of calcite occurs when the concentration of calcium ions and carbonate ions in the water exceeds the solubility product of calcite, which is approximately 3.3 times 10 to the negative ninth at 25 degrees Celsius. This can occur when water warms up, since the solubility of calcium carbonate decreases with increasing temperature, which is the opposite of the behavior of most other minerals, or when carbon dioxide is lost from the water through degassing or photosynthesis by aquatic organisms. In marine environments, limestone is commonly formed through the accumulation of the calcareous shells and skeletons of organisms such as corals, brachiopods, bryozoans, echinoderms, foraminifera, and coccolithophores. Coral reefs, which are among the most productive and diverse ecosystems in the modern ocean, are responsible for the production of enormous quantities of calcium carbonate, and ancient reef limestones can be found in the geological record dating back to the Cambrian period, approximately 540 million years ago. The Great Barrier Reef of Australia, which extends for approximately 2,300 kilometers along the northeastern coast of Australia and covers an area of approximately 344,400 square kilometers, is the largest living reef system in the world, and it produces approximately 100 million metric tons of calcium carbonate per year. Micrite, which is an abbreviation of microcrystalline calcite, is a fine-grained limestone composed of calcite crystals smaller than 4 micrometers in diameter. Micrite forms through the accumulation of very fine carbonate mud, which can be produced by the breakdown of calcareous organisms, by the direct precipitation of calcite from seawater, or by the mechanical abrasion of larger carbonate grains. Sparite, by contrast, is a coarser-grained calcite cement composed of crystals larger than 10 micrometers in diameter, and it typically fills the pore spaces between larger carbonate grains such as fossil fragments, ooids, and pelloids. The relative proportions of micrite and sparite in a limestone provide information about the energy level of the depositional environment. Limestones deposited in low-energy environments tend to be micrite-rich. Because the fine carbonate mud was able to settle out of suspension, while limestones deposited in high-energy environments tend to be sparite-rich. Because the wave or current action washed away the fine mud and left behind a framework of coarser grains that was later cemented by sparite. Ooids are small, rounded grains, typically between 0.25 and 2 millimeters in diameter, that are composed of concentric layers of calcite or aragonite precipitated around a nucleus, which may be a sand grain, a shell fragment, or another small particle. Ooids form in shallow, warm, agitated marine environments where the water is supersaturated with calcium carbonate, and the concentric layering is produced as the ooids are rolled back and forth by waves and tides, allowing calcite to precipitate evenly on all surfaces. A limestone composed primarily of ooids is called an oolitic limestone, or simply an oolite, and such rocks are characteristic of shallow marine platform environments. The Bahama Banks, which are extensive shallow water platforms surrounding the Bahama Islands in the Atlantic Ocean, are a modern environment where ooids are actively forming in water depths of less than 2 meters. Dolostone, which is also sometimes called dolomite after the mineral of which it is composed, is a carbonate sedimentary rock composed primarily of the mineral dolomite, which is a calcium-magnesium carbonate with the chemical formula CmgCO3 The formation of dolostone has been a subject of considerable debate among geologists for more than a century, a controversy that is sometimes referred to as the dolomite problem. The difficulty arises from the fact that dolomite is thermodynamically stable under surface conditions and should, according to chemical principles, be able to precipitate directly from seawater, which contains sufficient concentrations of both calcium and magnesium ions. However, direct precipitation of dolomite from seawater at surface temperatures has been extremely difficult to achieve in laboratory experiments, and it appears that most dolostone in the geological record was formed through the process of dolomitization, in which pre-existing limestone is converted to dolostone by the replacement of calcium ions with magnesium ions. This replacement is facilitated by the flow of magnesium-rich fluids through the limestone, which can occur in a variety of settings, including the mixing zone between fresh groundwater and seawater in coastal environments, the evaporation of seawater in restricted marine basins, and the circulation of magnesium-rich fluids through deeply buried sedimentary sequences at elevated temperatures. Chert is a chemical sedimentary rock composed of microcrystalline or cryptocrystalline silica, primarily in the form of the mineral chalcedony, which is a fibrous variety of quartz. Chert is extremely hard, with a Mohs hardness of approximately 7, and it fractures conchoidally, producing sharp edges that have been exploited by humans for the manufacture of tools and weapons for at least 2.6 million years, as evidenced by the stone tools found at Oldoway Gorge in Tanzania. Chert can form through several mechanisms, including the direct precipitation of silica from silica-rich waters, the replacement of pre-existing carbonate rocks by silica-bearing fluids, and the dissolution and reprecipitation of the siliceous skeletons of organisms such as diatoms, radiolarians, and siliceous sponges. Bedded chert, which occurs as continuous layers interbedded with other sedimentary rocks, is commonly associated with deep ocean sediments and is thought to have formed from the accumulation of siliceous microfossils on the ocean floor. Nodular chert, which occurs as irregular, rounded masses within limestone or other host rocks, is thought to have formed during diagenesis through the replacement of the host rock by silica-rich fluids. Evaporites are chemical sedimentary rocks that form through the evaporation of water from restricted basins, such as landlocked seas, lagoons, and playas, in arid climates. As water evaporates, the concentration of dissolved minerals increases until the solubility of individual minerals is exceeded, and they begin to precipitate out of solution. The order in which minerals precipitate is determined by their relative solubilities, with the least soluble minerals precipitating first and the most soluble minerals precipitating last. In a typical evaporating basin of normal seawater, the first mineral to precipitate is calcite, when the water has been concentrated to approximately 1/2 of its original volume. Gypsum, which is hydrated calcium sulfate with the chemical formula CaSO4 times 2H2O, begins to precipitate when the water has been concentrated to approximately 1/5 of its original volume. Halite, which is sodium chloride with the chemical formula NaCl, the mineral that constitutes common table salt, begins to precipitate when the water has been concentrated to approximately 1/10 of its original volume. The most soluble evaporite minerals, such as sylvite, which is potassium chloride, and carnallite, which is potassium magnesium chloride hexahydrate, precipitate only under extreme conditions of evaporation. Gypsum is one of the most common evaporite minerals, and it can occur in several forms, including massive gypsum rock, selenite crystals, which are large, transparent, tabular crystals that can reach spectacular sizes, and gypsum rosettes, which are clusters of lenticular crystals that form in sandy sediments. The Nica mine in the Mexican state of Chihuahua is famous for its Cave of the Crystals, which contains selenite crystals up to 12 meters in length and 1 meter in diameter, the largest crystals ever found on Earth. These crystals grew over a period of approximately 500,000 years in water that was maintained at a temperature of approximately 54 to 58 degrees Celsius by geothermal heating. When gypsum is buried and heated, it can lose its water of hydration and be converted to anhydrite, which is anhydrous calcium sulfate with the chemical formula CaSO4. This conversion typically occurs at temperatures above approximately 40 to 60 degrees Celsius, depending on the pressure and the salinity of the associated fluids. Halite is the second most common evaporite mineral after gypsum, and it forms in environments of extreme evaporation where the water has been concentrated to a very high degree. Halite deposits can be of enormous thickness. The Permian Age salt deposits underlying the city of Hutchinson, Kansas, in the United States, are approximately 100 meters thick and extend over a large area of the subsurface. The Dead Sea, which is located on the border between Israel, Jordan, and the Palestinian territories, is a modern example of a hypersaline lake in which halite is actively precipitating. The salinity of the Dead Sea is approximately 340 grams per liter, which is approximately 10 times the salinity of normal seawater, and the surface of the lake lies approximately 430 meters below sea level, making it the lowest point on the Earth's land surface. Evaporite deposits have significant economic importance, as they are the primary source of table salt, gypsum for the construction industry, and potash for the fertilizer industry. Organic sedimentary rocks are those which are composed primarily of the remains of organisms or of material produced by biological processes. Coal is the most economically important organic sedimentary rock, and it forms from the accumulation and preservation of plant material in swampy, oxygen-poor environments where the rate of organic production exceeds the rate of decomposition. The process of coal formation, which is known as coalification, begins with the accumulation of dead plant material in a swamp or bog, where it is partially decomposed by bacteria and fungi to form peat, a soft, brown, fibrous material with a carbon content of approximately 50 to 60%. As the peat is buried by overlying sediment, it is subjected to increasing temperature and pressure, which drives off water and volatile gases and progressively increases the carbon content and the calorific value of the deposit. The successive stages of coalification are lignite or brown coal, which has a carbon content of approximately 60 to 70% and a calorific value of approximately 10 to 20 megajoules per kilogram, subbituminous coal, with a carbon content of approximately 70 to 77%, bituminous coal, with a carbon content of approximately 77 to 90% and a calorific value of approximately 24 to 35 megajoules per kilogram, and anthracite, which has a carbon content of more than 90% and a calorific value of approximately 30 to 35 megajoules per kilogram. The great coal deposits of the world were formed primarily during the Carboniferous period, which lasted from approximately 359 to 299 million years ago, a time when much of the Earth's land masses were covered by vast tropical swamp forests, dominated by giant lycopsid trees, seed ferns, and horsetails. The Carboniferous period is, in fact, named for these coal deposits, with the name being derived from the Latin word carbo, meaning coal. The reason that coal formation was particularly prolific during the Carboniferous period is thought to be related to the fact that the lignin-degrading white rot fungi, which are the primary agents of wood decomposition in modern ecosystems, had not yet fully evolved, and as a result, dead plant material accumulated in vast quantities without being efficiently decomposed. This hypothesis was proposed by researchers who noted that the diversification of white rot fungi, based on molecular clock estimates, coincided approximately with the decline of coal deposition at the end of the Carboniferous period. Oil shale is another organic sedimentary rock of considerable economic interest, and it is a fine-grained sedimentary rock that contains significant quantities of kerogen, which is a waxy, solid mixture of organic chemical compounds that can be converted to liquid hydrocarbons through the application of heat. Oil shale differs from conventional petroleum source rocks in that the kerogen in oil shale has not been subjected to sufficient temperatures to convert it to liquid oil through natural processes, and it must be heated artificially, typically to temperatures of approximately 450 to 500 degrees Celsius, in a process known as retorting, to extract the oil. The Green River Formation of Colorado, Wyoming, and Utah in the United States contains one of the largest deposits of oil shale in the world, with estimated resources of approximately 1.5 to 1.8 trillion barrels of oil equivalent. Although the economic and environmental feasibility of extracting this oil on a large scale remains a subject of debate. Diagenesis is the collective term for all of the physical, chemical, and biological changes that occur in sediment after it has been deposited and before it is subjected to the temperatures and pressures associated with metamorphism. Diagenesis encompasses a wide range of processes, including compaction, cementation, dissolution, recrystallization, replacement, and orthogenesis, which is the formation of new minerals within the sediment. The boundary between diagenesis and metamorphism is not sharply defined, but it is generally placed at temperatures of approximately 200 to 300 degrees Celsius and depths of approximately 5 to 10 kilometers, depending on the geothermal gradient. Compaction is the reduction in volume and porosity of a sediment due to the weight of overlying material. In clay-rich sediments, compaction can reduce the porosity from an initial value of approximately 60 to 80% to values of 10 to 30% or less, and the associated reduction in thickness can be 50% or more. The water that is expelled from the sediment during compaction can carry dissolved minerals and contribute to the cementation of adjacent, more porous sediments. Cementation is the process by which dissolved minerals precipitate in the pore spaces of a sediment and bind the grains together, converting the loose sediment into solid rock. The most common cementing agents are silica, calcite, and iron oxide. Silica cement, which is composed of quartz that precipitates in the pore spaces and on the surfaces of existing quartz grains, produces some of the hardest and most resistant sedimentary rocks. The silica is derived from the dissolution of siliceous organisms such as diatoms and radiolarians, from the dissolution of feldspar and other silicate minerals during weathering and diagenesis, and from the pressure dissolution of quartz grains at their points of contact, a process known as pressure solution or chemical compaction. When silica precipitates on the surface of an existing quartz grain in the same crystallographic orientation as the original grain, the resulting overgrowth is called a syntaxial overgrowth. And the boundary between the original grain and the overgrowth may be marked by a thin line of inclusions known as a dust rim. Calcite cement is the most common cement in carbonate rocks and is also found as a cement in some sandstones. Calcite cement is precipitated from calcium carbonate saturated groundwater, and it can completely fill the pore spaces of a rock, reducing the porosity to near zero. The source of the calcium carbonate may be the dissolution of aragonite shells, which are thermodynamically unstable under surface conditions and tend to dissolve and reprecipitate as the more stable calcite polymorph, or the dissolution of calcite from other parts of the sedimentary sequence and its reprecipitation in a new location. The conversion of aragonite to calcite during diagenesis is a process known as neomorphism, and it can result in the destruction of the original microstructure of fossil shells while preserving their overall shape. Iron oxide cement, which is composed of minerals such as hematite and guthite, imparts a characteristic red, orange, or brown color to sedimentary rocks. Iron oxide cement is precipitated from iron-bearing groundwater in oxidizing conditions, and it is particularly common in continental sedimentary sequences deposited in arid and semi-arid environments. The distinctive red color of many desert sandstones, such as the famous red rock formations of the Colorado Plateau in the southwestern United States, is due to thin coatings of hematite on the surfaces of the sand grains. Coatings that may be only a few micrometers thick, but which are sufficient to impart a vivid red coloration to the rock. The formation of these iron oxide coatings is thought to occur during early diagenesis, when iron released from the weathering of iron-bearing minerals such as biotite, hornblende, and magnetite is oxidized and precipitated as hematite in the warm, dry conditions of the depositional environment. The process of dissolution during diagenesis is the removal of soluble minerals from the rock by the action of pore fluids, and it can significantly increase the porosity and permeability of a sedimentary rock. In carbonate rocks, dissolution is particularly important because calcite and aragonite are readily dissolved by acidic fluids, and the resulting secondary porosity, which includes vugs, molds, and channels, can be a significant contributor to the total porosity of the rock. The dissolution of unstable aragonite shells and their replacement by calcite is a common diagenetic process in limestone, and it can result in the creation of moldic porosity, in which the original shell shape is preserved as a void space within the rock. In sandstones, the dissolution of feldspar and other chemically unstable grains during diagenesis can create secondary porosity that enhances the reservoir quality of the rock, a process that has been documented in numerous petroleum-bearing sandstone formations around the world. Recrystallization is a diagenetic process in which the crystals of a mineral are dissolved and reprecipitated in a larger or differently oriented form without a change in mineral composition. In limestones, recrystallization can convert fine-grained micrite into coarser-grained sperry calcite, a process known as a grading neomorphism, and it can obliterate the original texture and fossil content of the rock. The driving force for recrystallization is the reduction in surface energy that accompanies an increase in crystal size, since larger crystals have a lower ratio of surface area to volume than smaller crystals, and the process is facilitated by the presence of pore fluids that can dissolve and transport the mineral in solution. Replacement is a diagenetic process in which one mineral is dissolved and simultaneously replaced by a different mineral, preserving the original texture and fabric of the rock while changing its mineralogy. Silicification, in which carbonate minerals are replaced by silica, is a common replacement process that produces chert nodules within limestone sequences, and dolomitization, the replacement of calcite by dolomite, has already been discussed in detail. The concept of diagenetic facies recognizes that different parts of a sedimentary basin may experience different diagenetic histories depending on their burial depth, the composition and temperature of the pore fluids, and the original composition of the sediment. Near-surface diagenesis, which occurs at depths of less than approximately 100 meters and temperatures of less than approximately 25 degrees Celsius, is dominated by processes such as the dissolution of aragonite, the precipitation of calcite cement, and the oxidation of organic matter. Shallow burial diagenesis, at depths of approximately 100 to 1,000 meters and temperatures of 25 to approximately 70 degrees Celsius, is characterized by compaction, pressure solution, and the formation of quartz overgrowths and authigenic clay minerals. Deep burial diagenesis at depths greater than approximately 1,000 meters and temperatures greater than approximately 70 degrees Celsius involves more extensive chemical reactions, including the conversion of smectite clay minerals to alite, the generation of hydrocarbons from organic matter, and the formation of late-stage carbonate and sulfate cements. Other types of cement that are less common but still significant include dolomite cement, siderite cement, which is iron carbonate, pyrite cement, which is iron sulfide and which forms under reducing conditions in the presence of sulfate-reducing bacteria, and clay mineral cement, which forms through the precipitation or transformation of clay minerals in the pore spaces of sandstones and other coarse-grained rocks. The type of cement that develops in a particular sedimentary rock is determined by the chemistry of the pore fluids, the temperature and pressure conditions, the composition of the surrounding sediment, and the biological activity in the subsurface environment. The identification and characterization of cements in sedimentary rocks is of considerable practical importance in petroleum geology, because the type and distribution of cement directly influence the porosity and permeability of potential reservoir rocks, and therefore their capacity to store and transmit hydrocarbons. Stratigraphy is the branch of geology that is concerned with the study of rock layers, or strata, and the processes of layering. And it is through the principles and methods of stratigraphy that geologists have been able to reconstruct the long and intricate history of the Earth's surface environments from the evidence preserved in sedimentary rocks. The most fundamental principle of stratigraphy is the principle of superposition, which was first clearly articulated by the Danish scientist Nicholas Steno in 1669 in his work Dissertationis Prodromus, and which states that in an undisturbed sequence of sedimentary rocks, each layer is younger than the one beneath it and older than the one above it. This principle, which may seem obvious to the point of banality, is in fact of profound importance, for it provides the basis upon which the relative ages of sedimentary rocks can be determined and upon which the geological timescale has been constructed. It should be noted, however, that the principle of superposition applies only to sequences that have not been overturned by tectonic forces, and geologists must be careful to determine whether a particular sequence is in its original orientation or has been inverted, a determination that can often be made by examining the sedimentary structures within the rocks, such as graded bedding and cross-bedding, which have a known relationship to the original way-up direction. A closely related principle is the principle of original horizontality, also attributed to Steno, which states that sedimentary layers are originally deposited in a horizontal or nearly horizontal position. Therefore, if sedimentary layers are found to be tilted or folded, this indicates that they have been disturbed by tectonic forces after their deposition. The principle of lateral continuity, the third of Steno's laws, states that sedimentary layers originally extend laterally in all directions until they thin out or terminate against the edges of the depositional basin. This principle allows geologists to correlate sedimentary layers across large distances, even when the layers are no longer physically continuous, provided that they can be identified by their distinctive characteristics such as lithology. Fossil content, or position within the stratigraphic sequence. The concept of facies, which was introduced by the Swiss geologist Amanz Gressle in 1838, refers to the sum total of the characteristics of a sedimentary rock unit that reflect the conditions under which it was deposited. Lateral changes in facies, which are called facies changes, reflect lateral variations in the depositional environment, and they are governed by Walther's law, which was formulated by the German geologist Johannes Walther in 1894, and which states that the vertical succession of facies in a stratigraphic sequence reflects the lateral succession of depositional environments. In other words, the facies that are found superimposed vertically in a stratigraphic section are the same facies that were laterally adjacent to each other at the time of deposition. This law is an extremely powerful tool for the interpretation of ancient depositional environments, for it allows geologists to infer the spatial arrangement of environments from the vertical arrangement of rock types observed in a single outcrop or drill core. Fossils, which are the preserved remains or traces of organisms that lived in the geological past, are found almost exclusively in sedimentary rocks, and they constitute one of the most important and informative types of evidence available for the interpretation of Earth's history. The process of fossilization requires that the remains of an organism be rapidly buried by sediment before they can be destroyed by decomposition, scavenging, or physical processes, and for this reason, the fossil record is heavily biased toward organisms that lived in or near environments of active sedimentation, such as shallow marine settings, floodplains, and lake margins. The most commonly preserved fossils are the hard parts of organisms, such as shells, bones, and teeth, which are composed of minerals that resist dissolution and decay, while soft-bodied organisms are only rarely preserved, typically under exceptional conditions of rapid burial and anoxia. The use of fossils for the correlation and relative dating of sedimentary rocks is based on the principle of faunal succession, which was first established by the English surveyor and geologist William Smith in the late 18th and early 19th centuries. Smith observed that the same types of fossils were consistently found in the same layers of rock, regardless of the geographic location, and that the sequence of fossil assemblages followed a definite and recognizable order from older to younger rocks. This principle allowed Smith to construct the first geological map of England and Wales, which was published in 1815, and it remains the basis for biostratigraphy, which is the use of fossil assemblages to correlate and date sedimentary rocks. Certain types of fossils are particularly useful for biostratigraphic correlation because they are found over a wide geographic area and are restricted to a narrow interval of geological time. Such fossils are called index fossils or guide fossils, and examples include trilobites for the Paleozoic era, ammonites for the Mesozoic era, and foraminifera for the Cenozoic era. The absolute ages of sedimentary rocks are more difficult to determine than the absolute ages of igneous rocks, because the minerals in sedimentary rocks were formed at the time of crystallization of the parent igneous or metamorphic rocks, not at the time of deposition of the sediment. However, the ages of sedimentary rocks can be constrained by dating igneous rocks that are interbedded with or intrude into the sedimentary sequence, such as volcanic ash layers, which are deposited rapidly and simultaneously over large areas and can be dated using radiometric methods such as potassium-argon dating, argon-argon dating, and uranium-lead dating. Volcanic ash layers that have been dated radiometrically serve as time markers within the stratigraphic sequence, and they allow the absolute ages of the surrounding sedimentary rocks to be estimated with reasonable precision. Sedimentary rocks serve as an unparalleled archive of the Earth's environmental history, recording changes in climate, sea level, atmospheric composition, and biological evolution over billions of years. The chemical composition of sedimentary rocks, the types of minerals they contain, the nature of their sedimentary structures, and the fossils preserved within them all provide clues about the conditions that prevailed at the time of their deposition. For example, the presence of glacial tillites in the geological record indicates periods of widespread glaciation, and such deposits have been found in rocks dating back to the Paleoproterozoic era, approximately 2.4 to 2.1 billion years ago, during the Huronian glaciation, and in the late Neoproterozoic era, approximately 720 to 635 million years ago. During the Cryogenian period, when the Earth may have been almost entirely covered by ice in a condition known as snowball Earth. The evidence for snowball Earth conditions includes the presence of glacial deposits at low paleolatitudes, the occurrence of cap carbonates, which are thick layers of carbonate rock that were deposited immediately above the glacial deposits and are thought to represent a rapid warming event, and geochemical anomalies in the carbon isotope record. The Grand Canyon of Arizona, in the southwestern United States, is one of the most famous and spectacular exposures of sedimentary rock in the world, and it provides a remarkably complete record of nearly 2 billion years of Earth's history. The canyon is approximately 446 kilometers long, up to 29 kilometers wide, and more than 1.6 kilometers deep, and it was carved by the Colorado River over a period of approximately 5 to 6 million years. The oldest rocks exposed at the bottom of the canyon are the Vishnu schist and Zoroaster granite, which are metamorphic and igneous rocks approximately 1.7 to 1.8 billion years old. And these are overlain by a sequence of sedimentary rocks, the Grand Canyon supergroup, which ranges in age from approximately 1.2 billion to 740 million years old. Above an erosional surface known as the Great Unconformity, which represents a gap of approximately 300 million years in the geological record, lies a sequence of Paleozoic sedimentary rocks that includes the Tapeats sandstone, A beach sand deposited during the Cambrian period approximately 525 million years ago, the Bright Angel Shale, a marine mudstone deposited in a shallow sea, the Redwall Limestone, a massive cliff-forming limestone deposited during the Mississippian period approximately 340 million years ago, and the Kaibab Limestone, which forms the rim of the canyon and was deposited in a shallow sea during the Permian period approximately 270 million years ago. The White Cliffs of Dover, which rise to a height of approximately 110 meters along the coast of Kent in southeastern England, are composed of chalk, a soft, white limestone that is made up almost entirely of the microscopic shells of coccolithophores, which are single-celled algae that live in the upper layers of the ocean. The chalk was deposited during the late Cretaceous period, approximately 100 to 66 million years ago, when much of Europe was submerged beneath a warm, shallow sea. The name Cretaceous itself is derived from the Latin word creta, meaning chalk, in reference to these extensive chalk deposits. The White Cliffs of Dover have served as a landmark for sailors and travelers for centuries, and they hold a prominent place in the cultural and historical identity of England. The chalk deposits of the Cretaceous period are not limited to England, but are found across a wide swath of Europe, from Ireland to Denmark to southern Russia, indicating that the shallow sea in which they were deposited covered an enormous area. The Burgess Shale, located in the Canadian Rocky Mountains of British Columbia, is one of the most important fossil localities in the world, and it has provided an extraordinary window into the diversity of animal life during the Middle Cambrian period, approximately 508 million years ago. The Burgess Shale is a fine-grained, dark-colored mudstone that was deposited at the base of a submarine cliff, and it preserves, in exquisite detail, the soft body parts of organisms that are not normally preserved in the fossil record, including worms, arthropods, chordates, and a variety of bizarre and enigmatic creatures that do not fit easily into any modern animal phylum. The Burgess Shale was discovered by the American paleontologist Charles Doolittle Walcott in 1909, and it has since been the subject of intensive study by paleontologists around the world. The exceptional preservation of soft-bodied organisms in the Burgess Shale is thought to be due to a combination of rapid burial in fine-grained sediment and anoxic conditions at the site of deposition, which inhibited decomposition and scavenging. The fossils of the Burgess Shale have fundamentally altered our understanding of the Cambrian explosion, which was the rapid diversification of animal life that occurred approximately 540 to 520 million years ago, and which produced the ancestors of most modern animal phyla. The economic importance of sedimentary rocks extends far beyond the coal and oil shale deposits that have already been discussed. Petroleum and natural gas, which together provide approximately 54% of the world's primary energy, are found almost exclusively in sedimentary rocks. Petroleum is formed from the remains of microscopic marine organisms, primarily algae and zooplankton, that accumulated in fine-grained, organic-rich sedimentary rocks known as source rocks. Over millions of years, as these source rocks were buried to depths of 2 to 4 kilometers and heated to temperatures of approximately 60 to 120 degrees Celsius. The organic matter was gradually converted to liquid hydrocarbons through a process known as catagenesis. The temperature range at which oil generation occurs is referred to as the oil window, and it corresponds to burial depths of approximately 2 to 4 kilometers, depending on the local geothermal gradient, which averages approximately 25 to 30 degrees Celsius per kilometer in most sedimentary basins. At temperatures above approximately 150 degrees Celsius, the remaining organic matter is converted primarily to natural gas, principally methane, in a process known as metagenesis. Once generated, petroleum and natural gas migrate upward through permeable rocks, driven by their buoyancy relative to the surrounding water-saturated rock, until they encounter an impermeable barrier known as a seal or cap rock, which is typically composed of shale, evaporites, or tight limestone. The petroleum and gas accumulate beneath the seal in a porous and permeable rock known as a reservoir rock, which is most commonly sandstone or limestone. The combination of source rock, reservoir rock, seal rock, and a structural or stratigraphic trap that holds the petroleum in place is known as a petroleum system, and the identification and characterization of petroleum systems is the fundamental objective of petroleum exploration geology. It has been estimated that the total volume of conventional petroleum resources in the world is approximately 2.5 to 3 trillion barrels, of which approximately 1.3 to 1.5 trillion barrels have already been extracted, and the remainder is distributed among known and undiscovered reservoirs in sedimentary basins around the world. Groundwater, which is water that is stored in the pore spaces and fractures of subsurface rocks, is another critically important resource that is largely hosted by sedimentary rocks. Aquifers, which are geological formations that are capable of storing and transmitting significant quantities of water, are most commonly composed of sandstone, limestone, or unconsolidated sand and gravel. The porosity of an aquifer, which is the fraction of the rock volume that is occupied by pore space, determines how much water the aquifer can store, while the permeability, which is a measure of the ease with which fluids can flow through the rock, determines how quickly water can be extracted from the aquifer. Sandstone aquifers typically have porosities of 5 to 30% and permeabilities that range over several orders of magnitude depending on the grain size, sorting, and degree of cementation. Limestone aquifers can have even higher permeabilities due to the dissolution of calcite by acidic groundwater, which can create extensive networks of caves, channels, and conduits through which water can flow rapidly. The Ogallala Aquifer, which underlies approximately 450,000 square kilometers of the Great Plains region of the United States, from South Dakota to Texas, is one of the world's largest aquifer systems, and it supplies approximately 30% of the groundwater used for irrigation in the United States. The Ogallala Aquifer is composed primarily of unconsolidated sand, gravel, and silt of tertiary age, and it contains an estimated volume of approximately 3,000 cubic kilometers of water, although this volume has been declining steadily due to withdrawals that exceed the rate of natural recharge. Sedimentary rocks also contain significant deposits of metallic and nonmetallic minerals that are of economic value. Banded iron formations, which are sedimentary rocks composed of alternating layers of iron oxide minerals and chert, were deposited primarily during the Precambrian Eon, between approximately 3.8 and 1.8 billion years ago, and they're the principal source of iron ore worldwide. These formations are thought to have been deposited in the world's oceans at a time when the atmosphere contained very little free oxygen, and the iron, which was dissolved in the ocean water in its reduced ferrous form, was oxidized to its insoluble ferric form by the oxygen produced by early photosynthetic organisms, principally cyanobacteria, and precipitated as iron oxide minerals on the ocean floor. The largest banded iron formation deposits are found in the Hamersley Basin of Western Australia, the Carajás region of Brazil, the Labrador Trough of Canada, and the Transvaal Basin of South Africa, and they collectively contain tens of billions of metric tons of iron ore. Phosphorite is a sedimentary rock that is rich in phosphate minerals, primarily apatite, and it is the principal source of phosphorus for the manufacture of fertilizers, which are essential for modern agriculture. Phosphorite deposits form in marine environments where upwelling of deep, nutrient-rich waters brings dissolved phosphorus to the surface, where it is concentrated by biological processes and precipitated on the seafloor. The largest phosphorite deposits are found in Morocco, which contains an estimated 50 billion metric tons of phosphate rock, representing approximately 70% of the world's total phosphate reserves. Sedimentary rocks are also the host of many deposits of other economically important minerals, including uranium, which is found in sandstone-hosted uranium deposits formed by the concentration of dissolved uranium by reducing agents in the subsurface, and manganese, which is found in sedimentary manganese deposits formed by the precipitation of manganese oxides from seawater. As this long and methodical examination of sedimentary rocks draws toward its conclusion, it is perhaps appropriate to reflect, briefly and without undue enthusiasm, upon the remarkable story that these rocks tell about the history of the Earth. Sedimentary rocks are, in a very real sense, the pages of the Earth's diary, and they record, in their mineral compositions, their textures, their structures, and their fossils, the events and conditions that have shaped the surface of this planet over more than 4 billion years of geological time. From the earliest known sedimentary deposits in the Isua supercrustal belt of Greenland, which provide evidence of liquid water on the Earth's surface at a time when the planet was still young and turbulent, through the banded iron formations of the Precambrian, which record the gradual oxygenation of the atmosphere by early photosynthetic organisms, to the great coal deposits of the Carboniferous, which preserve the remains of vast tropical swamp forests that covered much of the planet 300 million years ago, to the chalk deposits of the Cretaceous, which mark a time of warm seas and flourishing microscopic life, The story told by sedimentary rocks is one of constant change, of environments rising and falling, of seas advancing and retreating, of climates warming and cooling, of life evolving and diversifying, and occasionally suffering catastrophic setbacks. The study of sedimentary rocks is, fundamentally, the study of the Earth's surface processes and their interactions with the atmosphere, the hydrosphere, and the biosphere over geological time. It is a discipline that requires patience, attention to detail, and a willingness to consider evidence from many different sources and to integrate it into a coherent narrative of environmental change. The rocks themselves are patient, having waited millions or billions of years for someone to read the stories they contain, and they reward careful and systematic examination with insights into the workings of a planet that is far older, far more complex, and far more dynamic than it might appear to a casual observer standing on its surface on any given day. The sedimentary record is incomplete, of course, as erosion and metamorphism have destroyed much of what was once deposited, and the gaps in the record, represented by unconformities in the stratigraphic sequence, are sometimes as informative as the rocks themselves, for they indicate periods of non-deposition or erosion that reflect major changes in the tectonic, climatic, or eustatic conditions that prevailed at the time. And so, with this understanding of sedimentary rocks, their formation, their classification, their structures, their fossils, and their economic importance, one may begin to appreciate the quiet significance of the rock beneath one's feet, the layers of accumulated time that support the thin and fragile veneer of soil and vegetation upon which human civilization depends. Every grain of sand on a beach was once part of a larger rock, perhaps a granite or a gneiss, that was weathered and eroded and transported by water or wind to its present location, and it may, in the fullness of geological time, be buried and compacted and cemented into a new sandstone, which will itself be weathered and eroded and recycled into yet another generation of sediment, continuing the slow and endless cycle of creation and destruction that has been operating on the Earth's surface for more than 4 billion years, and that will continue, presumably, for billions of years more, long after the concerns and preoccupations of human beings have been forgotten and their own remains have become, perhaps, fossils in a sedimentary rock of the distant future. The processes that form sedimentary rocks are, by their very nature, slow and gradual, operating over timescales that are so vast as to be almost incomprehensible to the human mind. A single layer of limestone, only a few centimeters thick, may represent thousands or tens of thousands of years of continuous accumulation of calcium carbonate on the ocean floor. A thick sequence of sandstone may represent millions of years of sediment delivery from a distant mountain range that has long since been eroded away to a peneplain. The great unconformities in the stratigraphic record, where millions or hundreds of millions of years of geological time are represented by a single erosional surface, serve as humbling reminders of the immensity of deep time and of the transience of even the most substantial geological features. Mountains are raised up and worn down. Seas advance across continents and then retreat. Climates oscillate between greenhouse warmth and glacial cold, and through it all, sediment accumulates, layer upon layer. Recording the slow pulse of the Earth's geological heartbeat in a language of minerals and fossils and sedimentary structures that, with patience and skill, can be read and interpreted by those who have been trained to do so. It is, in the end, a remarkably mundane process, the settling of tiny particles out of water, or the precipitation of dissolved minerals from a supersaturated solution. And yet from this mundane process has arisen a record of unparalleled richness and complexity, a record that has allowed scientists to reconstruct the history of life on Earth, to understand the mechanisms of plate tectonics and mountain building, to locate and extract the energy resources that power modern civilization, to predict the behavior of groundwater systems upon which billions of people depend, and to gain insights into the workings of planetary processes that operate on scales of time and space that are far beyond direct human experience. The study of sedimentary rocks is, in this sense, a study of the Earth itself, of its past, its present, and, by extension, its future, and it is a subject that, while perhaps not immediately thrilling, is of a depth and significance that, one ventures to suggest, more than compensates for its somewhat staid and methodical character.